Hello everyone, my name is Jaap Nienhuis. I'm going to talk about models for inlet formation and migration on storm timescales and geologic timescales. Before I begin, I'd like to mention that I work with a lot of great postdocs and graduate students in my lab, and we study not only tidal inlets but also barrier coasts and river deltas on slightly longer timescales from 10 to 1,000 years. Looking mostly in the use of very simplified models, some of which I will highlight in this talk. So looking into inlets, there are three main questions that I'd like to go into today. First is, why do they form? Second is, why do we see inlets move, so migrate along coastlines? And third is, why does it matter? What are some of the longer timescale implications of these dynamic effects of tidal inlets? And so first is, why did they form? And some of these dynamics are very nicely shown in this video here. We see a migrating inlet, but slightly to the north you see this ephemeral inlet as well that is formed during storms but quickly closes up again on the timescale of months to years. So we recently published a paper, me together with Leonie Heikers and Gerben Rusink in JGR Surface, where we looked at the contrasting response of storms on coastlines and how sometimes inlets form in response to storms. And when we contrast storms, we find that sometimes overwash deposits or washover deposits that develop. And this is, there are two before and after snapshots from Hurricane Sandy, the US East Coast, where we find a storm hit and in response to that, a washover fan developed here. But in another case, and this is the New Jersey coastline, the same storm did not result in a depositional response, but instead an erosional response, where washover currents and storm surge eroded much of the barrier and resulted in the formation of an inlet. So why does this happen? What we did is form a very simple Del3D model of an idealized barrier where we have the ocean on the left side and a lagoon on the right side. And when we run this model for about 24 hours, so the typical duration of a storm, and we let the water level on the ocean side rise above the elevation of this gap in the barrier island. What happens in that case, when we use a relatively low storm surge, we see that a flow develops across the barrier. Sediment is eroded from the dune gap and builds this washover fan here that I showed in that picture before. However, we can contrast that with a case of a much higher storm surge here, where you see the same washover flow develop across the barrier island, but when the storm recedes, there is the barrier is breached and the response is erosional. So we can successfully replicate some of these observed dynamics with Del3D experiments. And why does this happen? Well, we dove a little bit deeper into the Del3D experiments, and what we did is we compared the amount of sediment transport by this flow across the island against the barrier volume, so the amount of sediment actually within the subaerial barrier. In this case of a low storm surge, there was some washover flux, but much less than the barrier volume. So the barrier was still had a positive volume, so it was still intact after the storm. This is very different from this high storm surge case, where there was much more washover flux in the subaerial barrier volume, and so there was a negative volume after the storm, so a breach occurred in this case. So using these simulations, we can then identify the causes of these changes in washover fluxes and the relevance of storm surge versus other things like vegetation, and better understand why barriers breach in some cases. Other interesting things that we look at in my lab is barrier or is inlet migration here that you see hundreds of meters per year over timescales of decades. And this inlet along the US Outer Banks moving towards the southwest. We studied this, me together with my thesis advisor, Andrew Ashton, published it also in JGR. We did also a simplified Del3D experiment with a pre-existing inlet, in this case, along a barrier coastline. And we forced this model with tides moving up and down, as well as waves that came in from an angle, and set up a longshore sediment transport along the barrier. So this is that same model, but then just showing you from the top, and I'll run this model shortly. Waves come from the top right and set up an alongshore current. And when we run that model, we see that an inlet develops, and then sediment deposition happens on the updrift flank and erosion on the downdrift flank, pushing this inlet down on the time scale again of years. Also, you see this nice flood tidal delta that develops in response to that storm. Looking a bit closer into this model, you see what I'm plotting you here is tidally averaged sediment transport fluxes. So these big arrows show wave-driven transport into the inlet along the updrift flank. And you see that these arrows slowly become less as the transport fluxes moves around the updrift flank. So there's deposition here resulting from the decrease in sediment transport fluxes. On the downdrift flank, on the other hand, you see that fluxes are pointing into the inlet or into the lagoon and are also increasing. So this indicates erosion here. That sediment is being transported first into the lagoon and then via the throat out and continues its way down toward the downdrift barrier. And so extending from these Del3D simulations that we can study, we can then form, again, a bigger scale picture of what happens here. And what we found to be particularly important is how the littoral transport that is fed into the inlet is distributed between a proportion that actually adds to barrier growth, a proportion that adds to flood tidal delta growth, and a proportion that bypasses the inlet completely and continues its way down. And if all of the sediment is bypassing, you can understand that none of it contributes to inlet migration, and therefore the inlet will not migrate. You see some of these dynamics also when we change basin depth, where very shallow basins constricted, a lot of the sediment is bypassed, and there's not much migration compared to a slightly deeper basin depth case. So why does it matter? What are some of the bigger and longer timescale implications of barrier and inlet morphodynamics? We studied that in a model that we developed with Jorge Lorenzo Trueba at Montclair State. And what I'm showing you here is a snapshot from that model with an initial barrier here and an upland area. And these are much longer timescales that I'm about to show you. So hundreds to thousands of years with also sea level rise. So these inlets in this case are freely allowed to move along this barrier island and move fluxes from the beach inland, and that can help these barriers maintain themselves in the face of sea level rise. So I'm showing you a video snapshot here, and you see inlets in this model run, again with waves that come here from the bottom of the screen, move, set up an alongshore current and move inlets back and forth. And not all migration rates are the same, so inlets can crash into each other, and sometimes new inlets might form and other inlets might close up. So very rich dynamics of these inlets and sediment dynamics that also affect how this barrier responds to sea level rise. Because what we can do is we can use another simulation where we have faster sea level rise rates, for example, or different tidal dynamics. We see that in this case, islands are not able to maintain themselves with sea level and are drowned very quickly. So to conclude, there are three things that I touched on in this talk. First, why do inlets form? Well, we find what is important is the amount of sediment transported across an island during a storm. And if that exceeds the volume of the barrier itself, the storm is likely to erode this barrier down to sea level and leave a breach. So leave a tidal inlet that might persist over time or might close up again after the storm. Second, why did they move? Well, we find that wave and tidal conditions create zones of deposition along the updrift flank. And if that coincides with erosion along the downdrift flank, inlets can migrate. And inlets can migrate much faster if a bigger proportion of the alongshore sediment transport is captured in that updrift flank of the inlet. Second, or third, sorry, why does it matter? Well, of course, there are big engineering and management concerns about inlet morphodynamics and inlet closure, but also inlets, by building these big flood tidal deltas, represent an important landward sediment flux, so flux from beaches to the lagoon that can help barriers move landward and respond to sea level rise. With that, thank you very much, and curious about your questions.